Hello all of you. So in the last few lectures, we have been discussing how can we analyze the liquid solutions, especially their mixing and phase separation behavior using the idea of Helmholtz free energy density. And we have been able to relate that quantity with the osmotic pressure and chemical potential, and all of them can be considered to be a driving force for the mixing or for phase separation. So now we will try to complete the other part of the story, is how will I actually get that function f of phi, right? So we know that once we have that and the double prime of that, the second derivative is, if it is more than 0, then we have mixing behavior, otherwise we have phase separation behavior and so on. We discussed that in detail, that if you give me the form of f of phi, I can tell you what is the mixing and phase separation behavior, but we haven't so far discussed how will we derive that particular expression, how will we get that expression. So with that will be the story that I will start again for liquid solutions, but we will go in the next week to the molecular simulation part, that also in some sense is giving me the Helmholtz free energy density, perhaps more rigorously than what we are discussing right now. So what we will discuss is known as the lattice model of solution, where my solute and solvent will occupy positions on a lattice, right? So before I even get there, let us first try to see like why exactly we have to make a model, where we started with saying that if I know the molecular motion, let's say if you have a system of molecule and I know the molecular motion and I know the kinetic energy and potential energy, I mean, if I have the energy, I can get the molecular motion, and then we have, I would say, the properties that we are interested in, right? Although that idea is quite valid, the only difficulty is that it cannot be applied to very large number of molecules. It is computationally impossible, at least for microscopic systems that we are typically interested in, right? So with that, why there is a need for a new model and how exactly we are building the model will be the part of the story I will discuss this week, and later on I will return to this problem, the actual problem where molecules are moving under influence of forces from other molecules, and try to say that if I do a simulation, I can also get the same quantity, perhaps more rigorously, right? So the basic idea behind both these approaches is that we are trying to get what is known as the classical Hamiltonian, that is the statistical mechanics way to describe energies. So Hamiltonian is actually a function as opposed to the energy that is a value, right? So Hamiltonian is described as the sum of the kinetic energy and the potential energy of the molecules. So let's say if you have n molecules in the system, they will have a kinetic energy and there will be some energy in the system that is going to change as the position of the particles change, right? A more common way to write the first part is to use the idea of momentum. We can write it as pi square by 2mi, because momentum is mass multiplied with the velocity. And the reason we prefer that representation is that I can then write the first term, that is my kinetic energy term, as some function of the momentum variables, right? So the way to think about it is there are two kinds of variables in the system that characterize the system. One is the momentum of particles and the second is the positions of the particle, right? So as the system evolves over time, or even in a state of equilibrium, since the molecules and particles still moving, we are having many possible configurations corresponding to different positions. Accordingly, we can have many different momenta of particles according to the history of the collisions. Every time a collision takes place, momentum is being exchanged. That results in change in momentum over time, so as to speak, even in a condition of equilibrium, because equilibrium is not a frozen state. So, if I really have to think about it, I can say that my Hamiltonian happens to be a function of the position and momentum, and now I am looking at Hamiltonian as a function of that, and that function will have how many variables? We will have, for each of the n particles, we will have 3 coordinates if we are working in 3 dimensions. So, you will have 3 n variables and 3 n variables also of the momentum, because momentum also is a vector. So, in total we have 6 n variables. These 6 n variables is what is referred as the phase space. Why? Because Hamiltonian is changing as a function of all these 6 n variables, right. So, as any of the position of any of the molecule changes, the Hamiltonian changes. As any of the momentum of any of the particle changes, the Hamiltonian changes. So, in totality, there are 6 n variables in that particular function, which pretty much determines the state of a system, right. And this is what we call a phase space. By the way, this phase has nothing to do with the phase separation that we have been discussing. In this case, we are looking at really the molecular states as opposed to the bulk phases that we have discussed earlier. So, essentially, just to think of like the complexity of this, let us say we were looking at just one molecule, n equal to 1. That is clearly not a thermodynamic system, and let us say this molecule is moving in only one dimension along a line, right. Let us say if a molecule is there, just for sake of hypothesis, we assume that it is moving along a line in any particular direction, it can go left or to the right, right. So, how will I characterize this molecule, or I have been using the word particle because it can be an atom or a collection of molecules. We will come to these things later, but for all that we are discussing, we are referring it to as particles. So, I can characterize this as some of its position, let me call it some r, and its momentum, and now the momentum is in terms of only one component because it can only go in one direction, right. So, there is one momentum and one position variable characterizing this particle. Now, over time, this particle can go to any position in space, to be precise. It can keep moving. If I wait until infinite time, it can go from this part of the universe to a different part of the universe. Similarly, it can have a whole range of possible momentum values, in fact 0 to infinity or minus infinity to plus infinity, if I also consider the sign of the velocity. So, with that in mind, if I have to represent where the molecule is at any particular state, it can be anywhere in this RP space. Each of these points refer to states available to the system. And although I have drawn only few points, the point is that I can pretty much put any point anywhere on this plot, and that will be a valid state of the system, because momentum can take any value and position can take any value, right. Now, under given considerations for a given system, it may not be from minus to plus infinity or 0 to infinity, it may be in a certain range, let us say from within like 1 meter to the left or 1 to the right, depending on a boundary condition like a wall, that is preventing the particle movement, or the momentum can also be limited. But the key point is that even in that limited range, the number of points which are possible are still huge. It can take pretty much any value in the continuous space. So, that is already complicated if I am looking at just one molecule. Now, we imagine that let us say if this molecule is moving in 3D. Now, we will have 3 variables characterizing the position of the particle and 3 variables characterizing the momentum of the particle. Now, if I start thinking along these lines, then position wise the particle can be anywhere, and similarly momentum wise the particle can be anywhere. And in fact, since for every given position I can have any momentum, in fact, although I have drawn it separately because I can only draw a 3-dimensional graph on board, the point is actually in reality we have a 6-dimensional graph, because for every position we can have any value of the momentum. So, this tells me that we have 6 dimensions for one molecule. Now, let us say what will happen if we have 2 molecules, right. So, let us say if we have 2 molecule in 1D. Now, you will have position of these 2 and momentum of these 2. So, now in totality you will have 4 variables to take care of. Now, if I do in 3D, we are going to have 12 variables, right. So, if I keep on extending the argument, in 3D we have in total 6n dimensions, and that even if I try to approximate by representing the continuous space by a discrete space, even then the number of possibilities are going to be extremely large, and that is the problem that we are trying to address when I am trying to represent the motion and the positions of particles, and using that to get the properties of interest in thermodynamics. So, there are 2 approaches to kind of go around this problem. I mean, this is the exact way of doing it, but clearly we cannot do that for a large collection of particles. So, there we have to find alternate ways of doing it, which have to be approximate, because the actual problem is computationally impossible, so as to speak. So, one of the ways is I can develop what is known as a TWI model, where I try to limit the phase space. I basically work with a much reduced phase space, and lattice model is an example of that. In fact, the random walk model of a drunkard who was going left and right, the example we did long back, was also an example of a TWI model, right. On the other approach is we can try to do a molecular simulation. Now, clearly we cannot do it for the actual system, but we can do for a smaller, I must say much smaller than actual system. With several numerical approximations. We will get to that molecular simulation part in the next week, but let us first look at the TWI model part of it and see how exactly it can achieve that, right. So, although I will discuss a lattice model for liquid solutions, the possibilities of TWI models are endless, right. You can imagine like many kinds of models, But keep in mind, these toy models are not really same as the actual system at hand, because we are working with a reduced phase space. Clearly, it can be at best a good representation of the system, but it cannot be the same as the system, right? For the toy model itself, I can get an exact solution or I can get an approximate solution, right? So, even if we are solving the toy model exactly, even in that case, we are not actually modeling the system, because as soon as I introduce a toy model, we are working on a reduced phase space, right? But for that particular model, I can get a correct answer. Let's say, for example, when I say a gas is an ideal gas, now within the assumptions of the ideal gas law, we can say PV equal to nRT, and that may very well be exact, assuming that we have point-like particles and we have no interaction. But that is not the reality, because in reality, we never have a point-like particles and we never have absence of interactions, right? So, we have to keep in mind that even if we are putting an effort into getting an exact solution of a toy model, it remains still far from the actual reality. At best, it is a good representation. At best, we can get qualitative behavior, but not really, I would say, quantitative behavior without some kind of like experimental input, and we can see later as we discuss that. In the molecular simulation part, it is slightly different paradigm. So, we are modeling a very small system, and for that system we can be close to exact within the numerical approximation we are making, right. So, in the toy model case, the model itself is an approximation. In molecular simulation case, the model is what the system is, except that we are doing it for a smaller system, right. Then we are applying some numerical approximation. For example, I can numerically integrate something, right. So, the numerical accuracy will increase as I am going for better schemes, or as I am going for like a larger systems and so on and so forth. But the model itself is representing the reality, right. So, that is the key difference. In the toy model case, we can get an exact solution, but even then it is far from reality. In the molecular simulation, even if we approximate numerically solution, we are getting actually a quantitative behavior, so as to speak, or we may get quantitative behavior that may be at least closer to the reality as opposed to a toy model, right. Having said that, I can also simulate the toy model. That is going to go towards a better solution of the toy model. If we cannot analytically solve it, we can go for a simulation of that. But even then, since the model is a toy model, we are still far from the actual solution, right. So, we have to understand these, I would say, 2 or 3 different paradigms. One is the molecular simulation, that framework wise it is modeling the exact system, but we can only do a very small system within certain numerical approximations. One is a toy model that can be exact, but it is not representing the actual system. For the toy model also we can do simulation, right. And in fact, we can use same tools of molecular simulation, let us say Monte Carlo and molecular dynamics, on the actual molecules and on the toy models. And in fact, as we go further in the discussion, what you will realize that in fact, everything to some extent is some sort of a toy model, but may be closer to the actual reality. But let us not get there right now, we will see as the discussion proceeds. So, with that kind of an argument, what the lattice model assumes is that I still have a system of solute and solvent, but I assume that they are occupying positions on a lattice. And lattice here is like kind of a chessboard, so as to speak. So we have a solute and a solvent. I will use different symbols for them. So let's say this is my solute and this is my solvent, right? So each of the cells can be occupied by the solvent. I am leaving some space for the solute. So all these cells can be occupied by a solute or a solvent. So let's say this is where my solvents are, and let's say this is where my solute are. You can already see some of the assumptions that we have already made while doing that in comparison to the actual system. So we already have assumed that my solute and solvent occupy cells on the lattice. So now imagine an actual situation. In actuality, you can have a continuous space where the solute and solvent can be anywhere. Now, if I have to elaborate what are the possible positions and possible momenta, that is going to be huge for the continuous space, in fact infinite. On the other hand, for the lattice model, since the positions of this solute and solvents are constrained to the cells like slots that I have assigned, now there are much fewer number of positions. Let's say if I am doing a 8 by 8 chessboard, we have only 64 positions where the particles can be. In the other hand, if the same area was occupied by a continuous kind of a distribution, then there are infinite number of ways I can place a particle, right? So by constraining or by limiting the positions that where the particles can be, we have actually got a huge reduction in the dimension of the problem we are trying to solve, right? That is the first advantage. That's why I say I am working with a reduced phase space. But nonetheless, if you notice here, I have tried to put the solute and solvent quite randomly, right? So we can think of, let's say if I have to think of an ensemble of this system, a thermodynamic ensemble, that will correspond to an ensemble of these lattices, and for each state in the ensemble, you will have different positions of solute and solvent. That is still possible. So at a qualitative level, we are accounting for the fact that the distribution of solute and solvent can be random, but we are getting a reduction in the dimension of the problem because we are representing a continuous space with a lattice, and that's, I would say, greatly simplifies the problem at hand. The second assumption that we make is that the solute volume is same as solvent volume, and that's already implicit from the diagram, and that is same as the cell volume. Let me call it Vc. Now, you may imagine a situation where you can try to make different kinds of cells, where a smaller cell will correspond to a smaller solvent, a larger cell will correspond to a larger solute molecule, or vice versa. But there is not too much benefit in doing that. First of all, it is going to be mathematically complicated. The reason why we were doing TWI model is because we wanted simplicity. And secondly, even when we do that, even then we are not very close to the actual system at hand, because an actual system was in a continuous space. So even by accounting for this small nitty-gritty that the volume of these molecules are different or volume of particles are different, we are putting so much numerical effort and modeling effort, and we are gaining very little in terms of the quantitative prediction. Unless the volume difference between solute and solvent is very large, that is probably not worth doing. Right. The last assumption that we make, and that is a very important one, is that interactions only occur between nearest neighbors. What this means here is, let us say if I want to focus on one of the solute molecules, let us say this guy, this can only interact with its 4 nearest neighbors that it finds, right, on the top, on the bottom, on the left, on the right, right. By the way, even though I have tried to draw a square lattice here, you may imagine that if I want to do a 3-dimension, I can draw a cubic lattice, right. If I want to have somewhat better representation, I can use a triangular lattice, right. The lattice form is not really very important here. That will not change the results that I am trying to discuss, right. So, in general, I can say that there are Z nearest neighbors. In this case, Z is equal to 4, right. You may as well ask that why not count the diagonal things. We can very well count that. That is only going to change my Z in the thing, right. So, if I also count the diagonals, then in that case we will have 8 neighbors, right. But the way the models are, it is always better idea to go for simplicity and try to improve the model only if there is a need in terms of the qualitative behavior you want to predict, right. If the lattice model is still good enough to give me a good picture, then why make some other model, right. So, this idea is that we have substantially, I would say, to a very large degree reduced the phase space. We have reduced the dimensionality of the problem, and once we have done that, then I am making some more approximations around it, right. Now, once we have got the final results for this kind of a model, we can go back and compare with the actual results if we have available, and try to improve the model later on than doing it in the very beginning. Because as soon as we can keep on adding the nitty-gritties, the model starts becoming more complicated. It is always good to have a good enough reference case. Let us say an ideal gas model serves like a very good reference case. Using that, I can develop a van der Waals gas model. Similarly, we can start with this model as a reference case, and I can include more features like effect of the volumes of solute and solvent, the interactions which are not between nearest neighbors, and so on. So, while doing that, essentially what we are capturing is only the short range interactions. So, if the molecules or particles have, say, only van der Waals interactions, the van der Waals are rather short range. They exist only over a small distance, right. So, molecules which are farther enough are anyway going to have lesser influence. Only the close enough molecules will have a significant influence on a particular molecule or particle, right. So, we should keep in mind that this model is therefore by design applicable only when we have short range interactions. Again, we could have included that, but you can imagine that it will make the simulation much more complicated, because the number of pairs simply become large, right. So, as of now, every molecule have only Z neighbor. So, in total we are looking at Z multiplied with n tot divided by 2 pairs, because every pair we will double count if I multiply n tot with Z, right. So, right now we have only these pairs. If on the other hand, if I am counting interaction between all possible particles in the system, we are going to have in total something like n tot square multiplied with some prefactor pairs, right. So, that will really make our whatever derivation I am doing or simulation I am doing on the toy model more expensive than in comparison to what we are trying to do. So, with this particular idea, I can then define these interactions as the following. I can say epsilon pp, epsilon ss and epsilon ps represent the solute-solute, solvent-solvent and solute-solvent interaction energy. So, if I will have to find the total energy of the system, assuming that it is at equilibrium, there is no external agency and so on, we can say that the total energy is something like epsilon pp multiplied with npp plus epsilon ss multiplied with nss plus epsilon ps and ps, where these represents the number of contacts. So, npp is the number of solute-solute contacts, nss is the number of solvent-solvent contacts, and nps is the number of solute-solvent contacts, right. Now, the 2 points here, that the first point is that this is going to be applicable only to a particular configuration, because as soon as the positions of the solute and solvent changes, the number of contacts also changes, right, and therefore, we need to say it that it is applicable only for a configuration that I call some I, right. So, for that configuration I can define the EI, right. The other thing is that this is only the potential energy of a system, because in the model so far we have not discussed the momentum of the particles, right, and there is a reason why we did not do that. The reason is like, since we are fixing the position of the molecule, the molecules can only move, so as to speak, by moving from one position to the other, right, and that is, I mean, like intuitively speaking, it is going to be from one slot to a nearby slot, right. So, in this construction, there is no scope to include changes in momenta and all these factors, because that velocity will give me a position that is like not lying on these slots. So, what is the meaning of talking about a momentum when the positions are pre-specified, where a molecule can only jump from one side to the other. So, in some way we are also constraining the movement by constraining the positions in the system, right. So, as of now we do not have the momentum in the system, we are only looking at the potential energy, or we only look at the configurational part of the energy. The next is going to be the kinetic part of that, but we will show that it is not so consequential for what we are trying to discuss. So, with that I wanted to conclude the discussion today. In the next lecture, you will introduce what is known as a mean field approximation that further simplifies that problem, and using that we can then evaluate the partition function for this lattice model, and once we have the partition function, we can clearly find the Helmholtz free energy and the Helmholtz free energy density, and once we have that, we can talk about the mixing and phase separation of solutions, and once we have obtained that, then we can compare with what we were expecting, or if we have any experimental results, is the qualitative trend same as the experimental results, and using that we can be convinced that our model is correct, and if that does not happen, then we have to build a new model, right. So, any intuition based toy model we are developing is as good as the results of the model. If the results are convincing enough, then the model is good. If the results do not work, then we have to think of a new model or try to see which assumption in the model need to be lifted to have a more convincing representation of what is going on. So, with that I wanted to conclude here. Thank you.